In this video, we're going to begin talking about integrals of multivariable functions. The first step in order to do this is to be explicit and define what we mean by an integral of a multivariable function. In particular, we're going to define what we mean by a double integral. In single variable calculus, when the integral was introduced, it was motivated by wanting to compute the area under a curve. And the way that the area under a curve was computed was by breaking up the region into a lot of rectangles, computing the area of the rectangles, and adding those areas together. Once that was done, that formed a Riemann sum, and a limit was taken to increase the number of rectangles and make it larger and larger, and the value that sum approached was what we called the integral. And we're going to do the same thing here for multivariable functions, except instead of computing area under a curve, we're going to compute the volume under a surface. Right, so to get started with this, let's suppose my function f of xy is defined on a rectangle. And so eventually we will do general regions, but we're going to start with rectangles. So the rectangle is going to be given by x ranging from a to b and y ranging from c to d. Right? And we're going to write this so we don't have to keep writing the intervals like this. We're going to just write this as the interval a cross b, the interval a to b cross the interval c to d. So whenever you see this notation, it simply means we're looking at the rectangle where x lies between a and b and c and y lies between c and d. So we want to break up the interval a to b into subintervals. Of equal width. And we can call this width whatever we want. Let's just call it dx. Right. We also want to do the same thing to the interval CD. We just want to call the width dy. Right. So we've broken up AB and CD into subintervals. And by doing that, we have actually partitioned up our rectangle into a grid of rectangles, smaller rectangles. So now we have this region R, the rectangle A to B and C to D. We have this region split up into a lot of smaller rectangles. In each of those, we're going to choose a point. Right? So we're going to choose a point, and I'll just call it xij star and yij star. All right, so this will be the point in the ith rectangle, or the ith row and jth column of our rectangle, of our grid. So we're going to choose a point in each rectangle. And from that point, we're going to form a column over the rectangle with the height given by the function value of the point that I just chose. So the height is going to be given by f of xij star, yij star. So now in this rectangular grid, we have little rectangle columns at each over the small rectangles. And so we're going to compute the volume of the column. And then to get the entire volume, the approximate volume, we're going to add up the volume of all of the columns in each of the rectangles in the grid. Right? So we're going to sum up all the volumes. And when we do that, right, we're going to sum up j equal 1 to m. So let's say there were m rectangles on the y direction. We're also the sum I equal 1 to n, where n is the number of rectangles on the x direction, of xi j star yi j star. So that's our height. Our width of a rectangle will be dx dy. And so we want to add up this sum here, and this would be our approximation for our volume. Now, before we go on to actually define a double integral, let's take a look at a picture of what we just did. Right, so here is the graph of a function z equals f of xy, that's the blue, and it's defined over a rectangle in the plane. So notice in the plane we have a green rectangle ranging on the x-axis from a to b, and on the y-axis from c to d. So in this picture, we have partitioned up the interval from a to b into, looks like 5 small subintervals, and also the interval from c to d has been partitioned into 5 small subintervals. That then forms a grid, so rectangle R is now a 5 by 5 grid. And in each of those little rectangles, we're going to form a column like the red one. That red one was formed by putting a base of the rectangle on base of the base of the column on the rectangle in the grid. And the height was chosen by picking an arbitrary point in that grid and looking at the function value at that particular point. And so what we would do is we would create a red column at each of the 25 rectangles in the grid, compute the volume of those rectangles, and add them together. And that would approximate the volume under this blue curve above the xy plane. So in this sequence of pictures at the bottom, on the far left, we have a function that looks a lot like the one we just looked at the top. We have a 5 by 5 grid underneath there, and we have all the rectangles. And you can see that those rectangles, those columns do come close to approximating the volume under that surface, but they're of course not completely accurate. There's definitely area under the surface that's not covered by the rectangles. In the second image at the bottom, we've increased the number of rows and columns. We've broken up more subintervals both in the x and y directions, and we see that we get a better approximation. And in the third picture over there on the right, we have even more subintervals on the x and y axis, and so we get an even more accurate picture. So in order to get the exact volume, just like with single variable calculus to compute the exact area under a curve, what we're going to do is we're going to take that summation that adds up all of these volumes of the columns, and we're going to take a limit of that in both directions. So we'll have to actually take two limits. One is the number of rectangles in the x-axis increases, and the other as the number of rectangles in the y direction increase. So we'll have to take that double summation, take a double limit, and that will be our double integral. All right, so our formal definition for this, we're going to be given a function, f of xy. For now, we want it to be defined on a rectangular region. Which we'll call R, which is simply the rectangle x goes from A to B, and y goes from C to D. The double integral of our function f over rectangle R is defined as follows. We're going to write as a double integral notation, so two integral signs, an R underneath denoting our region, and then our function f of xy, dA, where the differential here is with respect to area. And the definition of this is of course pretty confusing because we have a double sum. So we're going to start with that sum I wrote down earlier, the sum j equal 1 to m, the sum I equal 1 to n of xij star, yij star, dx dy. And this is our sum of the columns. And so we want to take both m and n, those are the number of subintervals in each direction. We want to take both of those as they get larger. So I want to take the limit as m goes to infinity, and also the limit as n goes to infinity. Right? So this is our definition of the double integral over f, of f over r. So it's this double summation and then a double limit taken of that. Right? Now, just like with single variable functions, once we define the integral and we look at this definition, we see that we never want to actually compute an integral using this definition. So in order to evaluate a double integral, to compute the exact volume under a surface, we obviously are going to need a better way of doing this. In order to find an efficient way to compute a double integral without having to go back and compute a double limit of a double Riemann sum, let's go back to the problem of finding the volume under a surface above a rectangle from a different perspective. All right, so in this perspective, what we're going to do is we're going to choose at each value of y in our interval c to d. So we're looking on the y-axis. At each value of y, we're going to let capital A of y be the cross-sectional area. So we're going to cut our surface at the plane corresponding to y on the y-axis, and look at that cross-section of our region that we're trying to compute the volume of, and compute the area of that cross-section. So if we define A of y in this way, the volume of our entire region above the xy plane and below the surface f of xy is going to be given by the integral of c to d of a of y dy. Right? So this is very obvious if you understand integrals of single variables. We're taking an area for each y between c and d and adding those areas together, and that is exactly how volume is defined. Right? And so volume in this case is now an integral of one variable, y. However, if we look at a of, let's pick a particular number, y naught, or y sub 0, then a of y sub 0 is that cross-sectional area. It's just going to be defined as the integral from a to b of the function f of x comma y naught dx. And here y naught is a constant, it's a fixed number, it's not a variable, so f of x y naught is actually a function of a single variable x. We've replaced the variable y with a constant. And so each of those cross sections is given by the integral of this function f. So if we put all of this together, we see that the volume is equal to the integral c to d of a of y dy. So this in turn, we can replace a of y with what we just found that it was equal to. It's equal to the integral from a to b of f of x comma y dx, all of that dy. And so if we just get rid of the grouping symbols here, we have the integral c to d, the integral a to b of this function f of xy dx dy. Right, so this integral here is this integral here is an integral that will compute our volume from what we've just seen above, and we're going to call this integral an iterated integral. And under the right conditions, we've seen here that this iterated integral would compute the volume and should be equal to the double integral that we were looking at previously, but again under certain conditions. Now, before we move on, we will look at a picture of this in a second as well. But before we move on, I want to point out we could also have started this process by, instead of choosing a point y, we could have picked a point x and computed the cross-section A of x, and then computed the volume that way. And if we had done that, and that's certainly a valid option to do, if we had done that and went through the same process, what we would have found is that f would be equal to the integral from a to b of the integral from c to d of f of xy dy dx. So this is a separate iterated integral. It's a different integral. If you notice, the integrals are computed in the reverse direction. And the dy dx are, of course, switched because the dy corresponds to the integral from c to d, and the dx corresponds from the integral from a to b. So if we switch the order of the integrals, the differentials have to change order as well. But this is a second iterated integral, and it is also a possibility to compute. It will also compute our volume. The question then is just, does it give us the double integral in all possible cases? And so we'll look at that shortly after we look at a picture of this cross-sectional approach. So on the left-hand side, we have our function f of xy defined on a rectangle R from a to b on the x-axis and c to d on the y-axis. And you can see on the y-axis there's a point y naught selected, and there is a cross-section taken there at y naught, and that's given by the orangish region. And so the function a of y naught would compute the area of that orange shaded region. If we then did this for all values of y naught between c and d, we'd compute the cross-sectional area at every point. That would give us the exact volume under this surface. On the right side is the exact same procedure, except that we're going to take the cross-sectional area at each x naught between a and b. And so here it's picked for a particular one. The area is there. We would compute the area of that cross section. Let it do this for every value between a and b. Add those together, and again we would get the volume under that under the surface. So we've seen two different ways to find the volume of the region under a surface above the xy plane. We've broken up the rectangle into a grid and used that to find the volume of various columns under the surface, and then sum up all of those column volumes. And we've also used cross sections along the y and x axis to do this volume as well. And so we know as long as this volume is positive and nothing weird is happening with the surface, all these integrals will be equal. However, whenever surfaces go below the xy plane and we have negative volumes, it's not clear that all of these integrals that we've developed will actually be equal to each other. But luckily, we have something that we call Fubini's theorem, which tells us that under a very slight condition, all of the integrals we've talked about so far will be equal. Right, so Fubini's theorem for rectangular regions says the following. Right, it says that if f of x is continuous on this rectangular region a to b and c to d, then the double integral over r that we defined previously is going to equal the iterated integral from c to d and from a to b of f of xy dx dy, and will also equal the iterated integral a to b c to d f of xy dy dx. So in other words, Fubini's theorem says as long as the function f is continuous on this rectangle, then all three of these integrals give the exact same volume. And so if we want to compute the double integral of a function, we can compute either of the two iterated intervals, and we have a choice. One of these might be a lot easier to compute than the other. And so we always have the choice of which one to use. Right, so for an example, let's say we wanted to evaluate the double integral of the function 15 minus x squared minus 2y squared dA over the rectangle R, which is going to be 1 to 5 halves cross 1 half to 2. All right, so we have this rectangle in the plane, and we want to look at the function 15 minus x squared minus 2y squared over that rectangle. Now, the first thing I want to look at here is to look at the function 15 minus x squared minus 2y squared. And I notice that that's a polynomial in two variables, and therefore it's continuous at every point in the plane. In particular, it's continuous in my rectangle, so I know that Fubini's theorem is going to apply. So in order to compute my double integral here, double integral of 15 minus x squared minus 2y squared dA, Fubini's theorem says we can compute either of those iterated integrals. In some cases, one of the iterated integrals might be a lot easier to compute than the other, but in this case, this function is pretty similar in terms of x and in terms of y. They're both x squared and y squared, and so we can really use either one. And so I'm going to do, on the outside, the integral from 1 to 5 halves, and on the inside, the integral from 1 half to 2, right, of our function 15 minus x squared minus y or minus 2y squared. And then what we have to watch out for is we have to make sure we have the differentials in the right place. So 1 half to 2, the innermost integral, corresponds to values of y. And so that means I want to differentiate with y's first and then by x, so I want dy dx. Right? So just to be very clear about this, this integral needs to correspond with this differential, and this integral here needs to correspond with this differential. Right? So whichever order we do, we need to make sure the integrals and the differentials are in the right place. All right, so now to compute this, we're going to keep the outer integral as an integral, and we're going to evaluate the integral that I sort of labeled in red here, the integral from 1 half to 2 of this function dy. So we're going to find an antiderivative in terms of y. When we do that, we want to think of x as a constant. So what we're really doing here is we're undoing partial differentiation. So when I antidifferentiate this function, we're going to get 15y minus x squared y. Remember, x squared is a constant in terms of y. And then minus 2/3 y cubed. And we want to evaluate this from 1 half to 2. And all of that is happening inside the integral with respect to x. Okay, so we have the integral from 1 to 5 halves. We evaluate this function at 2, and we're going to get 30 minus 2x squared minus 16/3. We're going to evaluate it at 1 half, so we're going to have 15 halves minus 1 half x squared minus 2/3 times 1/8, and that would be 1/12. All right, so we have the integral of this function. Notice that we are going to simplify the thing in the square brackets here, but notice that in the square brackets we now have a function of y, or I'm sorry, a function of x, which is good because we're differentiating that function as a single variable function with respect to x. So when you clean all of that up and you do the addition and subtraction, we end up with the integral from 1 to 5 halves of the function 69/4 minus 3x squared over 2 dx. Right? And now this is a straightforward single variable calculus integral. So we need to find an antiderivative in terms of x. So 69/4 x minus x cubed over 2. And we'll evaluate that from 1 to 5 halves. And so what we get 69/4 times 5 halves minus 125 over 16 minus 69/4 minus 1/2. And when you compute all of the fractional arithmetic here, we do get 297 over 16. Right? And so this is the value of our function, of our double integral that we wanted at the beginning. Fubini's theorem said it was equal to this value, which is 297 over 16. And since that function, 15 minus x squared minus 2y squared, is positive at every point in the rectangle R that we were considering, this is actually the exact volume under that surface along the rectangle, but above the xy plane. Right now, if you want to practice with this one, with something like this, what I would recommend that you try is try to compute this this quantity with the other iterated rectangle. So I did the integral where we differentiated with respect to y first and then x. Try setting up the integral where you differentiate with respect to x first and then y. And of course, all of the work in the middle should look different because you're going to have, instead of like at the top of this particular slide, we have a function of x. At that particular point in the other approach, you should have a function of y, and it should range from 1/2 to 2. But at the end of the day, you should still end up with 297 over 16. So I'd recommend you give that one a shot just to get your hands dirty with an example like this. We'll look at one more example like this. So let's say we want to evaluate the double integral over region R of the function 6xy squared minus 4y, okay, dA, where my rectangle here is 0 to 1 cross 0 to 2. And so the first thing that we're going to notice is that 6xy squared minus 4y is a polynomial again, so this is going to be continuous, so Fubini's theorem is going to apply. Now, before we go on and compute this, one thing to point out is that this function, unlike the previous one, this function is not always positive on the rectangle R. For example, when x is equal to 0, this function is just equal to negative 4y. So along that point where x is 0, all of those function values are going to be negative. So this particular integral will not compute the volume under the surface. It'll compute what you might call the signed volume. Any volume that's under the surface but above the xy plane will be counted positively. Any volume that lies under the negative or under the xy plane will be counted negatively. And then it will add those signed numbers together and take the positive volume, and it'll take the negative volume, and it'll combine them and give you the net volume in that sense. Right? So I just want to point that out because sometimes if you think of these being volumes, if you don't get a positive result, sometimes that throws off people's thinking. But remember, these could be negative, they could be positive, it could be 0, lots of different options. Okay. All right, so now to actually compute this integral, again, we're going to want to use an iterated integral. And again, we can think about what we want to do. I'm going to do the integral from 0 to 2 on this one first, and then the integral from 0 to 1. So 0 to 1 is x, so I want to do dx first and dy. Right? And now we just compute. So the inner rectangle is with respect to x. So I need an antiderivative of that with respect to x. So 6xy squared, we have an x, so we're going to increase the exponent and divide by 2. So we're going to have 3x squared y squared. And then minus 4yx, or 4xy, if you want to keep the x's first, just because negative 4y is a constant in terms of x. And so we'll differentiate that from 0 to 1. And when we do that, when we substitute in 1, we're going to get 3y squared minus 4y. And then when we substitute 0 in, we get 0 in both cases, because both have a factor of x. So we get the integral from 0 to 2 of 3y squared minus 4y dy. And so this becomes y cubed minus 2y squared, evaluated from 0 to 2, which looks like 8 minus 8, and then substituting in 0 yields 0, and 8 minus 8 is exactly 0. Right? So you'll notice that the arithmetic here is a lot simpler than the previous one because we did not have fractions involved. But the key here is that this double integral equals 0. And so what this tells us is that if we look at this particular function, 6xy squared minus 4y, over the rectangle R, there is some volume that lies above the xy plane, and there's some volume that lies under the xy plane, and that the amount that lies above the xy plane is exactly equal to the amount that lies below. Right? Now again, if you want to go back and compute this iterated integral in the other direction, I encourage you to do so, and you should also get 0 as the final value.